Okay, so before we get started, just a quick reminder that homework 5 is due this Wednesday. So I hope it's not too bad. Like if I remember correctly, one of the question is to essentially use your own words, rewrite one small part of the theorem, one of the theorem. I forgot which number, but essentially you want to prove that I think theorem 7.1. So you want to prove that the Euclid's fifth postulate implies the proposition 1.29. So I mean, the things that it's this, the whole goal that I assign whenever I assign like this type of like textbook problem, or for example, that sometimes I will assign like some of the cases from one of the textbook theorem. My goal is for everyone to go read that theorem to understand the proof. Like for example, the homework 4, you just turn it in, right? Like even proving the SSS, like this is one of the textbook thing, I can still tell that some of the students really either doesn't really fully understand the proof before the case 1, including the case 1, or actually didn't really read the proof before they write the proof for case 2 and case 3. So there's some mistakes. So if I have time, I will come back to discuss it. But later on, when you get the homework, you can also see the my comments here. Yeah, so you want 1 implies 2. So essentially, that's essentially the fifth postulate implies proposition 1.29. Yeah, so you should, I would say, like, to be on the safe side, you should definitely still read the textbook. Just do not rely fully on my notes, because my notes also follow the textbook, but you should definitely go back to read the textbook as well, just to make sure that you get the whole thing. Okay, so yeah, you're right. It's the statement 1 implies statement 2, which is essentially the statement 1 is the fifth postulate, and implied statement 2 is proposition 1.29. Okay, so as I said, that whenever I assign this kind of textbook like proposition or theorem, like especially prove one of the cases, you should definitely read through the whatever the theorem I assign, and then like understand the proof before you start it. So my goal today is to go over 7.4. So there are a lot of things included in 7.4. So there's no way I could cover it like every single one, but I want to pick out the most important ones. So a lot of them you probably already know, I mean, the fact-wise, not the proof. But I want to do some of the proof because it will give you some techniques that you will need later on. And for 7.5, unfortunately, there are also a lot of like construction things. So for 7.5, I'm going to only pick out pretty much 2 of the proposition. I think we should be able to cover one of them today, but the second one, which is a construction, I don't think I will have time today. I will leave it to Wednesday. So the goal, I can tell you like in advance that before midterm, my goal of midterm is to cover up to 7.6, and 7.6, which is essentially the Pythagorean theorem, and also the converse of the Pythagorean theorem. So yeah, so eventually we're going to reach, actually on Wednesday, we're going to start talking about 7.6, okay? So first of all, 7.4, actually most of them are essentially related to parallelogram, and also what's the area of the parallelogram, and also the relation between the area of the parallelogram and the half triangle, okay? So first of all, again, let me recall what's the definition for parallelogram, right? So parallelogram, the definition is that you have a quadrilateral, meaning a figure with 4 sides, right? Whose opposite sides are parallel. So which means you have 2 pairs of parallel sides, okay? And that's the definition of parallelogram. But it depends, so first, in order to get a parallelogram, you need to show me that you have a pair of 2 parallel sides. So the first thing, I think I mentioned the statement of this proposition last time. The first thing we can prove is that if you have a parallelogram, right? So in the parallelogramic area, we can prove the opposite sides and opposite angles are equal to one another. And also we can say the diameter of the parallelogram, it's going to bisect the area. Okay, so first of all, let's look at this picture ABCD. So first, we assume we already have a parallelogram. So that means we have the assumption where AB is parallel to CD, and also AC is parallel to BD. So in this case, so once we have a parallelogram, we can prove that the opposite side, AB, is going to equal to CD. And we also have another pair of opposite side, AC is going to equal to BD. And also opposite angles are also equal. So angle A is going to be equal to angle D, and also angle B is going to equal to angle C. And even more, the diameter is going to bisect the area, which means if you draw a diameter like BC or the other around, doesn't matter whether BC or AD, then the area is going to be the same. So here we can prove that the area of triangle ABC is going to be the same as area of BCD. Okay, so we actually need to prove quite a lot of things, technically 5 things, I would say. But you can, as you can imagine, like most of them should be done by proving 2 triangles are congruent, okay? So first of all, in order to save some time, I kind of already write down the proof. So, so hopefully that this will help us to be more streamlined here. So let me leave this picture here. So we're going to use it. So now to start the proof, right, we start with a parallelogram, right? So let's say that ABCD be our parallelogram, and we draw BC to be its diameter, okay? Okay, so now the first thing we can have, the proof is actually not that bad at all. Like we keep using the same fact over and over. So first of all, we know that because we already have a parallelogram, so one of the parallel sides is AB parallel to CD, right? And as you can see, this diameter BC cuts through these 2 parallel lines, AB and CD, right? So one of the proposition, this is actually what we just mentioned, one of the proposition 1.29, which is the statement 2 in the theorem 7.1, tells you that the alternate angles, the interior alternate angles are equal if you have a transversal cutting through 2 parallel lines. So this tells me that if you think of this BC as a transversal cutting through AB and CD, then this angle ABC is going to be equal to BCD. So this is the first thing we're going to have just by using the proposition 1.29 that we saw last week, okay? And by exactly the same reason, we have another pair of such alternate angle, okay? So first we look at AB and CD. Now we look at AC and BD, right? So same idea, AC and BD are parallels. And you can see that the same diameter BC cuts through these 2 lines. So we again can use the same philosophy by the same proposition that the alternate angles are going to be equal. But this time our alternate angle is this one, ACB and CBD. So again, we have another pair of alternate angles which are equal. And of course, they're essentially by the same proposition, okay? So now you can see from the picture, we have 2 pairs of angle are equal, right? So the red one are equal, and then also the green one are equal, okay? And now if you look at, so my goal is to compare the triangle ABC and BCD, right? I mean, which is like kind of already in the picture. And if you compare these 2 triangles, then we realize that we have a common side, right? Which is essentially my diameter, right? So now you have these 2 angles, 2 pair of angle are equal, right? And they're essentially from the alternate angles, and plus this common side BC, right? So now if you compare these 2 triangle here, can anyone tell me that how am I going to prove which triangle scheme I can use to show that these 2 triangles are congruent? Okay, I already saw one answer. Does anyone have like, so Joe says it's ASA, right? So you have A angle, side angle, right? So I hope there's no disagreement on this, right? So basically by angle, side angle, so I put the question mark here, so angle, side angle. So be careful, you need to, when you write the homework, right, when you cite a congruent scheme, please convince yourself, right? Like you need to convince me and convince yourself that you really have the criteria, right? you should not just depend on what I say or what other people say, right? Like I remember homework 3, I tell you use SAS, but some of you actually just give me wrong condition and it still says that this is by SAS, right? You can only use the congruent scheme when you really have the support evidence, right? You should not just randomly pick one because you think that's the one. Okay, you need to really convince yourself from the picture, you really see the correct evidence. So in this case, we have really like angle, side angle. So this by ASA, we have triangle ABC and DCB are congruent. So if it's congruent, then we can see right away, right? So now we have congruent. So let me just directly use this picture. Then if you have congruent triangle, right, then this side AB is going to be equal to CD, right? Because these two triangles are congruent. And we also have AC, which is going to be equal to BD, right? And these are directly from the fact that we just proved that two triangles are congruent. And on top of that, I also have angle A is going to be equal to angle D, right? And you can see that this is just by these three things, we already proved the first two, right? We want to prove AB equals CD. We want to prove AC equals BD. That's check. We also can prove the third one, angle A equals angle D. So right away, after you prove two triangles are congruent, you have the first three of the conclusion we want. Okay, now we need to do slightly more work on B and the last two. I mean, the last one is not too bad. So now we have AB equals CD. This is what I just said, right? This is all check mark because the congruence of the triangle. But now if you look at this, now we need to prove angle B and angle C are equal, right? But you can see that from the picture, angle C is just the red angle plus the green one. Same thing for B, right? So pretty much right away, you only need to write down one extra line. So essentially this is angle C, which is ACD, is the same as the red one plus the green one. And then you can see that we already know there's a pair of angle, right? So you can see that one of them is this ABC and BCD. The other is here, the second one. So let me put 1 and 2, right? We have two conditions that's already proved here. So then angle C is definitely equal to angle B, just by looking at the picture, like the information we already had. And regarding, so the number 4 is also proof. Regarding the area, right? Technically, we already have that. Why? Because we already proved that these two triangles are congruent, right? So we already know since these two triangles are congruent, so I mean, we already know that if it's congruent, then their area should be equal. And then this is essentially kind of given by the area postulate 3 that we already have. Okay, so I mean, technically we already had that, but since it's the last statement, so I want to leave it at the end. Okay, so technically you can see that this proof is not too bad at all. The only thing we use, actually the key fact we use is essentially by using the fact that AB parallel to CD and AC parallel to BD. And since if you have parallel lines, then most of the time you're going to see that some alternate angles are going to be equal. So you're going to have a lot of good property coming from it. Okay, so this one is not too bad. So this basically tells you if you can show this is a parallelogram, then right away you know a lot of angles are equal to each other, the opposite side are equal to each other, and also when you cut it half, you're going to get the same triangle with the same area. Okay, so any question for this proposition? Okay, so this should not be too bad. So now after we have that, I want to introduce several new terminology in this textbook. And some of them can be a little bit confusing, I mean, because it looks similar. So I want to emphasize this. So first of all, if you have picture like on the left-hand side, right? Maybe let's look at the first one on the left. So if two triangles, let me use different color. If two triangles or parallelograms, if we say they are in the same parallel, it just means that when their vertices are on a pair of parallel lines. So from the picture, you can say triangle ABC and triangle DBC are in the same parallel, because you can see that they're essentially, their vertex lies on the same pair of parallel lines, right? And you can also say that from the second picture, you can say that you have all this parallelogram you saw, right? Parallelogram ABCD and BCEF, or even GHJI, they are all in the same parallels. Okay, so you're going to see this terminology over and over in the textbooks throughout the literature. So when we say two triangles or two parallelograms are in the same parallel, that just means that they're in the same, along their vertices are on either one of the pair of parallel lines. Okay, so now this is not too bad, because this is essentially, you can draw the picture and see it, that's what it meant. But there's the definition 2 and 3 is something you want to make a distinguishment, because it can be very confusing at the first sight. So we say two triangles and two parallelograms, if they're already in the same parallels, then we say they're in the same, first one, we say they're on the same base. It means that when they share a side or share a base. So for example, I put an example here. If you look at the first picture on the left, ABC, oops, sorry. So triangle ABC and BCD, they share the side BC, right? And so that's why we say they're on the same base. When we say on the same base, it means exactly the same, they share the common side, okay? And we can also see, if you're talking about parallelogram, right, then I said that ABCD, the parallelogram ABCD and parallelogram BCEF is also sharing the same base, right? Because you can see that they share the same side or same base BC here, right? So we say parallelogram ABCD and BCEF, they're on the same base, okay? So one thing I want to make a remark here that, I mean, for triangle, we know that when we pick out the vertex, it have to be in the order. When you describe a parallelogram, how do I know which vertex is which? Usually, we need to follow the order, okay? It doesn't matter whether it's counterclockwise or clockwise. For example, for the picture on the left, the second one, right? If you want to describe the parallelogram ABCD, usually either we say ABCD or ADCB. You don't jump around the vertices. Otherwise, that I wouldn't know which one is the correct order, right? So you need to follow the order of the vertex when you describe it. And as you can see that I will use this little parallelogram picture to indicate that it's a parallelogram. Okay, so this is just a remark. When you're trying to describe a parallelogram, make sure you put the vertex in order, okay? And this is the second definition. Third definition, there's another terminology that you will see that they say the triangles or parallelograms are on equal base. Okay, so this time it's a little bit different, right? When we say on the same base, we mean they share a common side. When we say equal base, it means that it's not necessary that they share the same common side, but they would have a congruent side, meaning they will have two sides which are congruent or equal to one another. So for example, if you look at the first picture, we say that triangle ABC and EGF are on equal base, because here I assume BC is equal to EF. So this triangle ABC, or actually DBC, are on the equal base with triangle GEF, okay? So they're not necessarily sharing the same side, but the side they have are congruent to each other. That's why we meant equal, okay? And same thing you can say for the parallelogram. So if you look at BCEF in the second picture, and here we assume the side BC is equal to IJ. So we say that parallelogram BCEF and GHIJ are on equal base. Okay, so please make a distinguishment between on the same base and on the equal base. Okay, they may have the same conclusion or same property later on, but they mean different thing. Okay, one is that you need to really share a common side. the other is just means that they have a congruent side. Okay, so that's a different. Congruent means the measurement is equal, right? But they're not necessarily exactly the same thing. So you want to distinguish these two definitions here. So you're going to see this throughout the literature. So the first thing we can prove is that if you have two parallelograms which are on the same base means they really share a common side, okay? So if they're on the same base, plus if they're in the same parallels, right? So they lies along the same parallel lines, then they're going to have the same area. So from the picture here, you can see that I wrote down the area of the blue parallelogram is going to be the same as the area of the green parallelogram. And here, of course, I need to say that these two lines are parallel. They need to be in the same parallels, otherwise it's not correct. So from the modern knowledge, we already know this is true, right? This is not hard. The conclusion, we already know it's not hard to imagine, right? I mean, of course, we haven't proved it, but from what we know from high school geometry, we can imagine this is true because if they're in the same parallel, they're going to have the same height, right? And they share the same common base, so they're going to have the same equal base, right? The length of the base is going to be equal. So of course, later on we can prove that the area of a parallelogram is base times height. So from what we kind of already know from the high school geometry, we know this has to be true, okay? But we don't need to rely on the formula of the area for parallelogram. We actually can directly prove this fact before we even know the formula for the area, okay? So here, if two parallelograms share the same base, then they should have the same area. Okay, so how are we going to prove this? So we need the picture on the right here. So I give you more specific points here that we can use later on. So first of all, let me push a little bit upward here. So let's say we have two parallelograms, ABCD, and also EBCF, okay? And so first, we already see from the picture, they share the same base, okay? They're on the same base, which is the BC. But they're also in the same parallels because we know that they all lies on two parallel lines. One of them is AF, the other is BC, okay? So now we want to prove eventually that these two parallelograms that you saw, the blue and green one, are having the same area, okay? So now this one is a little bit longer proof, but pretty much we're also going to use all the things we have saw before. So let me start the proof here. So first of all, we definitely need to use the property of a parallelogram, right? So since we know that ABCD is a parallelogram, and we can use what we just proved, right? This is essentially what we just proved is proposition 1.34. We know that if we have a parallelogram ABCD, then the opposite sides are going to be equal. So first, we right away know AD equals BC, right? That's the first thing. And we have another parallelogram, BCFE, so we can do the same thing. So by same reason, we know, this time we know that EF is going to equal to BC, right? So this is just coming from the fact that we just proved, right? So we know that because we have two parallelograms here, so BC is going to equal to AD, right? By just now the proposition 34 that we just proved. But at the same time, BCFE is also a parallelogram, right? This is the assumption. So by the same proposition, we know that BC equals to EF. So now we know, adding these two together, like using these two facts, we know then it means AD equals EF, right? Okay. So now we have this information first, okay? Now why I need to first prove this? Because I'm going to use the segment AE, okay? So now if you look at this segment AE here, let me push it up a little bit. Oops, I want different color. So if you look at AE here, And also later on, I'm going to use DF, okay? So now let's see. So then we have, if you look at AE, this is essentially AD plus DE, right? But we just knew, or we just obtained that AD equals EF. And we keep the DE, right? So EF plus DE is going to be the same as DF, right? So right away, we also know that AE is going to equal to DF, okay? So now we have essentially AE equals DF, okay? Okay, so now let's see what else we can obtain, right? So now I also need another thing. I need AB to be the same as CD, okay? Because I'm going to prove that two triangles are congruent, okay? So, but if you look at AB and CD, this is just the other pair of opposite side of the parallelogram, okay? So let me write down what we have here. So again, oops. So since we know that ABCD is a parallelogram, right? So by the same proposition that we just did before, we can prove, we know that the opposite pair of the parallelogram is going to be equal, right? So AB is going to equal to CD. Okay, now you might wonder, okay, what two triangle I'm actually comparing? If you look at the picture, I'm actually comparing the triangle. I'm going to compare triangle ABE and triangle DC and F. Okay, so you can see that I already proved AE equals to DF. I also just proved AB equals CD. So I have two like equal sides, two pair of equal sides. The only thing I miss is another pair of equal angles. Okay, so I need to get that. Okay, so now let's see. So now how am I going to get an equal angles? So I need to go back to use that because I start with some parallel lines, all right? So what you can see, or actually what we're going to use is that if you look at this two parallel pair, right, AB and CD, because we start with a parallelogram. So if you look at this AB parallel to CD, and you think of that this AD cuts through these two parallel lines. So we are going to have two equal angles here. This is by one of the proposition we have done before, just because AB is parallel to CD. Okay, so let me write down what we have here. So since this is another information we need, since AB is parallel to CD, and the line AF or AD cuts through these two. Right? So this is actually by the same proposition 1.29. We can show, or actually we prove, that angle EAB is equal to angle FDC. Okay, so EAB is this one. I just put it down. And FDC. Okay, so now if you look at, let me put it out here, let me write the picture here. So essentially I have something like this. Let me pull out the picture so you can see more clearly, right? And you have another one, which is DCF, right? And we prove that AE equals DF, AB equals CD, and we also have this two angle here, right? So you can write away BE equals CF. BE equals CF. Yeah, I think you can use it. Yeah, because we have the same, yeah. I mean, it's not, it's, yeah, we can use SSS in this situation. Yeah. I mean, let me double check. Yeah, you can do that. Yeah. I mean, there's no one unique way. I'm just kind of follow the same way as the textbook, but you're right. We could definitely use the SSS in this case. Okay. So yeah, so actually when you do the homework, you probably sometimes notice that you have set maybe 2 or 3 different way, depends on which triangle scheme that you have here. Okay, so I'm just stick to one method. Okay, so now in this case, we essentially have SAS from the picture, but of course there might be other way to do it. So compare the true triangle. I just write down what I said, so for completion. Right? We have AE equals DF, and we just set AB equals CD, and angle equals this. So by SAS, angle ABE is congruent to DCF. Okay, so what's good out of this, right? So if they're congruent, then that means the area is going to be the same. Area. Okay, so now let's keep this in mind, right? Okay, so now what's the goal here, right? My goal is still trying to, I go back to this picture, I want to prove that the area of ABCD is the same as BCFE, right? But I just proved that this shaded region are the same, right? So you can see that they have some overlap, right? So I'm going to do some cut and paste, okay? So let me see. Okay, I'm going to write down, oh, actually I need space? Let me move the space a little bit down. I might need a little bit extra space here. Okay, so now let's see. We're almost done, the last part. So let me call G to be the intersection. I actually already put it in the picture, but let me be complete of the proof. That B be the intersection of BE and CD, right? And so now I want to see that the area of, I want to see the area of ABGD. I want to see the area of AB, G, and D. So the one that they don't overlap. Okay, so you can see that the 2 triangles overlap on middle triangle. So I want to see that the one that outside the overlapping triangle is the same area. Okay, so now let's see. Okay, so BA, oh, did I miss the angle? Let me see. EAB and FDC, CDF, same thing, angle CDF and FCD is the same thing. Oh, did I? Yeah. Okay, I think I just, yeah, I think that's right. Okay. Okay, so now let's see. So I want to claim that the area, so let me put it here. So the area of ABGD, sorry, I don't have the picture here. Let me finish writing, then I will go back to the picture. So probably you want to draw a picture on the side so you can follow what I have here. Okay, so what I want to do is essentially, if you go back to look at the picture here, right? So triangle ABE and DCF, we already know the area are the same because they're congruent. So if we subtract the middle overlapping triangle, which is DEG, then the remaining part is, I don't know what that shape is, some four-side shape. ADBG is going to be the same as CGEF, okay? And if that's the case, right, if we know that if the two triangle cutting out DEG, the middle triangle, the remaining shaded, the remaining part is equal, then now the only thing we need to do is to add this BCG onto it, then it will become the same area. So essentially, I use the two triangle just now, cutting the middle overlapping one. So the remaining two are equal. These two regions are equal, okay, these two. But now if I add the lower triangle BCG, then that becomes the parallelogram that we want, okay? So that's essentially the last step. So let me see. So the area of the parallelogram that we want is this area we just did. So the area of ABGD plus, let me be sloppy, just directly add it here, the triangle BCG, which is the same thing as ABGD is the same as GEFC plus the same triangle, which is essentially the area of the parallelogram we want on the other side, EBCF. Okay. Okay, sorry, I think because I'm moving back and forth, it's a little bit hard to compare. So I would suggest that the last part is really just comparing the overlapping part. You take your subtraction to get two same area. Now you add another common one. So you eventually get the two parallelogram to be the same. Okay, so I would say that please read the textbook because I mean, I'm not doing on the board, I'm doing on the computer. So sometimes it's hard for me to go back and forth. But like what I said, the proof here should be very straightforward. Once you have the two triangle are congruent, the below, anything follows is essentially cutting and paste some area here. Okay, so the offshot is essentially telling me if you have two parallelogram in the same parallels, right? And if they share the same base, then we know they have the same area, okay? So this is the first thing we know, and this is actually going to give us a lot of good information, okay? So now with all these 2 or 3 things we just proved in mind, then we can actually derive some formula. So remember, like back in section 7.2, that do we need to justify the subtraction with like a common notion? Yeah, technically, yeah, you should say that, yeah, if you subtract, that's by common notion 3, I believe. But I mean, at some point, I kind of just stop being a little bit sloppy, because if I really want to write down very like rigorously every step by step, then it's going to take forever. Yeah, but you're right. Technically, the reason we can do subtraction like that for the area is essentially by the common notion. Yeah, the common notion 3. Yeah. Okay, so with the things that actually I forgot this remark. Technically, if you really look at the proof of what I just did, the 1.35, actually, if you read the textbook later on, they're going to mention this remark that if you look at the picture, right, you need to question, is it always possible that when two parallelograms share a base, they're always in this relative position? It turns out that it's possible that when you draw the parallelogram, they, like, for example, if you look at the points A, D, E, F, they may not be exactly at the same order like what I drew here, right? So unfortunately, if I want to be super rigorous, right? So as what I wrote here in the remark, that the proof of this theorem actually depends on the order of the points A, D, E, F. So technically, I should consider other cases, right? For example, if you might draw a different picture where D may not lie in between A and E anymore. So, I mean, technically, I only prove one cases, right? But you can imagine other cases, the proof should be very similar. So I'm just going to kind of just use this one case as an example. But keep in mind that sometimes that you need to be a bit careful of the proof, right? So for example, like the SSS we just proved in homework 4, right? You can imagine it has 3 cases, depends on the relative position of the point B or G, right? So you can imagine sometimes when you draw the picture, if you're not careful enough, you might miss out certain cases. Okay, so just keep this in mind that we're only done the proof for one spatial case. So with all the things we have proved in mind, plus back in section 7.2, I actually kind of skip ahead, tells you some of the fact that we can use, even though it's not really in Euclid's element. Okay, I'm doing a little bit cheating, a shortcut that I essentially use more modern knowledge that was proved later on. And that will help us to build on some extra theorem, more advanced theorem that, that Euclid doesn't really include it. Okay, so you can see that this, as I said, if you see any results that was written as theorem rather than proposition, then those are the extra one that we added. Those were not in Euclid's element. The one that was in Euclid's element should be listed as proposition, I don't know, 1 point something, or later on proposition 3 point something. The proposition were already in Euclid's element, but those theorem is the one that we actually added later on. Okay, so theorem 7.3, I'm not going to prove it for the next couple theorem, but I can tell you just by telling you that it's a combination of the results that we already knew. So we can actually prove the area of a parallelogram with base B and height h is going to be B times h. And how do we derive this fact, right? If you have a picture like this with base B and a height h, right? The idea of this proof is by combining the theorem 7.2. What's 7.2? If you go back to section 7.2, it tells you that the area of the rectangle is the base times height, okay, which is the same thing here, B times h. And we are going to combine to use 7.2 and proposition 1.35. 1.35 is just this one that we just proved, right? So 1.35 says if you have two parallelograms which lies on the same parallel and sharing the same base, they're going to have same area. Okay, so now you can see the idea of the proof is here, right? You have a parallelogram, right? Let me draw the picture here. You have parallelogram, whatever that is, and you have a base B here, and you have height h. How do you prove the area is the same as the area of the rectangle? What you can do is just draw a rectangle here, right? If you have a rectangle, so this rectangle is going to have the same base as whatever the parallelogram you want, and with the same height, and they're in the same parallels, right? So by proposition 1.35, they should have the same area because they share the same base and are in the same parallels. But we already know from 7.2 that the area, if we assume 7.2 is proof is true, right? Then we already know the rectangle has area B times h. And then now by 1.35, we know these two shapes should have the same area. So that gives us the area of the parallelogram to be B times h. So by this kind of construction, using what we already proved, you can essentially prove that, yeah, indeed, this parallelogram and the rectangle has the same area. Okay, so this is basically coming from combining these two facts, nothing fancy. Okay, so we know now the area of the parallelogram is base times height. Okay, now we can further prove that the area of the triangle, right? Remember, the only thing we know so far is that if you look at a parallelogram cut in half, you can cut into equal triangle, right? You can cut into two equal area triangle. In other words, the triangle is half of the area of the parallelogram, okay? So now this should not be too hard to imagine that now once we know the formula of a parallelogram, we can know the area of a triangle with the same base and the same height, okay? And we can prove that the area is going to 1/2 base times height, okay? So you can see that, okay, let's say if you have this triangle with base B, height h, how are you going to use the fact we already proved to prove this, right? Then essentially, I mean, say we don't know anything about the area of the triangle yet, but we know the area of triangle is half of the area of the parallelogram if you double it, right? So the idea is on the existing triangle, you build up a parallelogram, right? So this is essentially parallel side, right? And so you can essentially see that we already know that if you have a parallelogram, if you draw a diameter, then these two triangles should have equal area, which means the triangle should have half area of this parallelogram. But we already know just now that the area for the parallelogram is b times h. Then of course half of it is 1/2 b times h. So again, it's essentially just simply using the proposition 1.34. We just said that the diameter cut the parallelogram in half, and then also use the formula for parallelogram. So you can see that we build on one onto another, right? So this can be built up, even though we already know the conclusion, but this can be proved based on the existing result. And after parallelogram triangle, what we can do is, if you can kind of combine this shape together, you will come up with actually a trapezoid, okay? So first, let me remind you what's the definition of trapezoid, okay? So trapezoid, this is more modern language, right? If you go back to read the Euclid's element, you don't see this terminology. We actually introduce later on. So the modern, I'm going to use the modern definition. I mean, there's some different definition in the sense that depends on how strict you want for the definition, but I want to just stick with one modern one. So a trapezoid is a quadrilateral with only one parallel pairs, right? So what would be a, so you only have one parallel pair, right? So it doesn't matter, maybe you have something like this, right? Or maybe something like this. These are all example of trapezoid, okay? Because they all have one parallel pairs, okay? Now, actually based on knowing the area for triangle and parallelogram, we can actually derive the area for trapezoid, even though we already know in our mind probably. So the area of a trapezoid with parallel base B1 and B2 as what I draw in the picture here, and base and an altitude height h, is half of the product of the altitude and sum of the base, meaning the area is 1/2 times B1 plus B2 times h, okay? And there are several ways to do this, to prove this by using existing fact. One way I can imagine is, because let's say you have some, whatever trapezoid you have, right? Let me just draw some random one, right? I can imagine, because these two are parallel sides. So if you extend the parallel lines, right? So what you can do is combining the fact of knowing the area of triangle and parallelogram. So I can imagine if you want to prove the area of trapezoid, which actually I'm going to assign it as a homework, one thing I could think of is you can build up a bigger parallelogram, right? Like what I draw in the picture. So on the existing like trapezoid, whatever it looks like, you can build a larger parallelogram, right? And you can see that the larger parallelogram is essentially consists of the existing trapezoid and adding a triangle, right? So if with the same information, you already know this is B1, this is B2, and this is H, right? So you know the larger area should be B1 times H. That's the larger parallelogram. And you can subtract the smaller triangle here, right? And since we know that this whole thing is going to be B1, so you know the remaining side, right? Then you can take out the triangle area. That will give you the trapezoid area, okay? So you can see that this is the scheme of how you're going to essentially prove the area of trapezoid based on knowing the area of parallelogram and triangle, okay? So this is not hard. You just need to kind of do a cutting and paste, something like this, okay? So you can see that now we know the area of trapezoid, triangle, and parallelogram. Okay. So now the next thing that I want to go back to what we start with is that we can not only we can show the parallelogram with the same base are equal to, like the area are equal. We can also show like a little bit more general. we can show that the parallelogram which are on equal base and in the same parallels are equal to one another. Okay, so as we can see that if I have these two parallelogram here, right, and I say they share the equal base. So let me remind you, equal base means that they share two sides which are congruent to each other, right, as in the picture. Then these two parallelograms should have the same area. Okay, so this is also not hard to prove it. So first, let's start with the picture on the right. I have this ABCD parallelogram and also EFGH, and they have the equal base. So because this is the assumption, right? I want them to have equal base, meaning I assume BC equals FG, right? And then they're in the same parallels, right? So essentially this line, L1 is parallel to L2. Now I join BE and CH. Okay, so let me use different color here. So I want to join BE and CH. My goal is to prove that the green parallelogram, the area, is going to be the same as the area of the blue parallelogram. But I'm going to draw this like kind of intermediate parallelogram, the red one I just drew, right, the BCHE. So I'm going to draw this intermediate one, and then I'm going to use this as a tool. Okay, oops. Okay, so first let's see, right? So we already have all the information here that we have BC equals FG and we have two parallels. Okay, so now let's see. So start from what we have. We know that EFGH is a parallelogram. So we can see that we are quoting this kind of the same proposition over and over. So by proposition 1.34, that we know if it's parallelogram, then the opposite sides are equal. So we know FG equals EH, right? So FG is going to be equal to EH, right? But we also know from the assumption that FG equals to BC, right? This is the assumption I just circled, right? So we also know FG equals to BC. That's essentially given as the assumption. So then we know, right? So BC equals FG, FG equals EH. So BC equals EH. Okay. So why I want to prove this? Because even you look at the picture, right? You look at the shape BCHE. We only know that at the beginning, EH is parallel to BC. But we don't know whether the two red lines, BE and CH, I don't know whether it's parallel or not. So before I can prove something, or before I use some proposition, I cannot directly say that BCHE is a parallelogram. I don't know yet. Okay, that's what I want to prove. I want to show you this intermediate shape is actually a parallelogram. Okay, so now we have BC equals EH, right? And at the same time, we know BC is parallel to EH. Right? So with the fact that BC equals EH, and also we know that by assumption BC is parallel to EH, then we can go back to use the proposition that I talked about I think last Wednesday, that this is 1.33. Okay, so what's 1.33? Remember that we talked about if you have like a quadrilateral, if you know that one opposite pair is parallel, but at the same time equal to each other, then it implies we can prove that the other pair should also, the other opposite pair should also be equal and parallel. Okay, so by proposition 1.33, sorry. By 1.33, we have actually the opposite side. So that's essentially BE and CH. Right? After using 1.33, that's when I know that this shape BCHE is a parallelogram, right? Before, I only know BC is parallel to EH, that's it. But since I also know BC is equal to EH, that's why I can use proposition 1.33 to say that the opposite pair are also equal and parallel. Once you have two parallel sides, right, then you can say that I have two parallel sides. So then that's when I, CH, oh, sorry. Yeah, thank you. Yeah, CH, thank you. Okay, so once I have that, then I can show that it's actually a parallelogram. So EBCH is a parallelogram. Actually, my computer is making problem. Okay, give me a second. Let me take care of this. Okay. Okay, so what now? So I have EBCH is a parallelogram. Okay, so now let's see. So now we can compare the area. Okay, give me a second. So now we say that if you go back, you can see, okay, first we have BCEH is a parallelogram. Now we can prove, right? So now if this is a parallelogram, then we're actually in a good shape because now we have three parallelograms, right? And you can see the middle one, BCHE, shared the same base as ABCD, right? But at the same time, BCHE also shared the same base as the blue parallelogram, right? So you can see that then the middle parallelogram should be have the same area as the green one and also having the same area as the right one. Okay, so let me just write down this. I hope my computer can last. It's stuck, like maybe getting too hot, so it's a little bit weird now. So okay, so now, so since EBCH share same base as parallelogram ABCD, right? So and actually I want to emphasize that they're in the same parallel and in the same parallel. Okay, if they're in the same parallel and share the same base, then by proposition, this is what we just talked about. This is 35. They have same area. So we know that EBCH should have the same area as ABCD by the same reason. Right? Then the area of parallelogram EBCH is going to have the same area of another parallelogram, which is EFGH. Right? So now, I mean, then we are done. So okay. Actually, I want to ask a quick question. From my side, I keep seeing my OneNote is kind of making trouble. It sometimes shows not responding. Do you guys also see the same thing? Like sometimes it would just freeze. Yeah, same. Okay. Yeah. So I mean, I don't know. Maybe my computer getting a little bit too hot. So it's okay. I think it can last for a bit, but it just maybe like every now and then it's going to freeze a little bit. Yeah. Different page. Oh wow. Okay, that's weird. Yeah, from my side, what I saw is that it kind of freeze and then jump a little bit. So let me know if you cannot see anything or I need to move around. Okay. So I'm trying to like hope it will last for now it become freeze again just now. Okay. So hopefully that's can get through everything. So okay. So now we prove so what we just proved, let me go back here. So 1.36, this is exactly what I proved. A summary of the proof is, if you look at the picture here, right? Essentially, I add these two lines, BE and CH, and that's the intermediate step, meaning I first want to show this BCHE is a parallelogram. Once I show that, I have three parallelograms here, which they're all lies in the same parallel lines. So then, okay, give me a second. Let me save this. I want to open close the OneNote and reopen it again to see whether it can fix this problem. Okay. Hopefully I can have all the things I want. Okay, so what am I? Okay, so once you have this BCEH as an intermediate parallelogram, then essentially, basically, I use what we just did. If you have two parallelograms which share the same base, then they're going to have the same area. So I use the middle parallelogram, right? And then shows that they have the same area as one of the parallelogram. And same thing, EHBC also share the same base as FGHE. So that's why they will have the same area. So the proof is quite straightforward. It's just you need to kind of build on from the fact that you already know. Okay, so the last thing I want to talk about in section 7.4 is that we compare two parallelogram with this, like either they share the same base or equal base, right? And we know that the outcome is the same. If they're in the same parallel, it doesn't matter whether they share the same base or equal base, they're going to have the same area. And you can imagine if we cut the parallelogram into half, then they're going to become a triangle. So intuitively, we should have the exact same property for triangles, which lies in the same parallels. So essentially, this propositions 37 and 38, which I'm not going to prove it because they're essentially using what we just saw. So we can conclude, we can actually prove the triangles which are on the same base and in the same parallel, they're going to have the same area. And same thing for proposition 38, it's going to tell you that triangle which having the same equal base and in the same parallels are also having the same area. So from the picture, if you have all these triangles lying on the same parallels, and I say the length BC is the same as EF, then so if you look at the triangle ABC and BCD, then they are the triangle which share the same base. So by proposition 37, they have the same area. But if you look at triangle ABC and EFG, those are the one in the same parallel, but with equal base, right? Because BC equals EF. But by proposition 1.38, they're going to have the same area. And I'm not going to do the proof because you can imagine the proof should be pretty much the same thing as what we saw for parallelogram, right? So you can imagine to prove this, what you do is essentially you build a bigger, a double like area parallelogram, right? Once you have you can compare the parallelogram, then you cut it half, that will give you the area of the triangle. So as you can imagine, the proof should be similar. One of triangle is just half of the parallelogram. Okay, that's why I'm not going to prove it once you have the same result for parallelogram, right, you should have the same thing for triangle. And one last thing in session 7.4 I want to show you is essentially, this is essentially a combination of the area of triangle and parallelogram. So it says if you have a parallelogram which have the same base with a triangle, right, and in the same parallel, then the parallelogram is double. Okay, so you can see that this is all related to each other, right? So I might probably say something wrong about the proof, but you can see that the proof for proposition 1.3738, shouldn't be too different from what we just proved. Okay, so and for 1.41, it's essentially relating the area of a parallelogram and a triangle. Okay, so basically you can see that, I mean, this is intuitive. So that's why I'm not going to prove it. There's so many small things that we can prove, but we don't have that much time. Okay, so for 7.5, as I said, I really only want to prove 2 things. And today, unfortunately, we are only going to have time for do one of them. So the first one is this 1.43. Okay, so this might be something a little bit spatial in the sense that you may not see this before, but intuitively from the picture wise, you can probably guess it or see it. Okay, so it tells you that in any parallelogram, the complement, okay, I will tell you what does that mean for complement. The complement of the parallelogram about the diameter are equal to one another. Okay, so first of all, what's the complement? The complement is actually the green shape that I'm doing here. So the complement is this part. The HKFD and EBGK are the complement. Okay, so why we say it's complement of something? So what's the parallelogram? From the statement I mentioned, parallelogram about the diameter. So the red shaded part, or you can say the parallelogram AEKH and KGCF are what we call the parallelogram about the diameter AC, right? You have a diameter AC, and along that you can, depends on where the parallel line EF is, you can definitely draw 2 parallelogram about this diameter AC. And then that's essentially along the diagonal or diameter. And off the diameter, you have this green region that I'm drawing here. This is essentially what we call the complement of those parallelogram. So essentially 1.43 tells you that we can prove the complement of this complement to a region having the same area. Okay, so you can imagine this should not be too bad. It's again like some kind of cutting and paste. Okay, so I think I already write down the proof so we can directly see it. Just let me put the picture up here. Okay, so now we say, okay, we have a ABCD as a parallelogram to start with, and we have AC as a diameter. Okay, and about AC, we will have 2 parallelogram, right? AEKH and also GCFK. Okay, those are the 2 parallelogram. And we call another 2 parallelogram BGKE and HKFD are the complement. Okay, so these are the complement. Okay, so now how are we going to prove it? This is actually also straightforward. You just need to kind of equal certain things. So again, by what we already saw before from previous section, the proposition 34, we know that the diameter always cut the parallelogram in half, right? So right away, if you look at the largest parallelogram ABCD, because we know AC is going to cut the ABCD in half, so right away we know the triangle ABC and ACD should have the same area. Okay, that's the largest triangle we can have. But by this exact same reason, if you look at the smaller parallelogram, let's say AEKH, right? Then AK also cut it half, right? So we are going to have triangle AEK, which is going to be the same as triangle AHK, the area, it's going to be the same. And exact the same reason, if you look at the other parallelogram about the diameter, which is KGCF, then the diameter KC is going to cut it half, right? So the area of triangle GKC is going to be the same as triangle KFC, okay? So now with all this 3 information, right? So let me remark it, 1, 2, and 3. Now I'm going to use these 3 conditions to prove that the off-diagonal part, the complements, are having the same area, okay? So you can see that the green part, the off-diagonal part, right? If you look at one of them, the left-hand side, if you look at BEKG, BKG essentially equal ABC, subtract the 2 smaller triangles, right? So you take EBGK, right? And you look at the area. It's going to be the largest triangle ABC. And you cut off the smaller AEK and the smaller KGC, okay? But we already know from the first 3 conditions that they're at the same time equal to all this triangle here, right? So it's going to equal to the one corresponding to the other side, right? So after you do the subtraction, right away, you know that it's going to be equal to the area of the other complement, okay? So basically, this is not that hard. Once you use the previous established fact that the diameter of a parallelogram would cut your area into half, then you do, again, this kind of cut and paste game. Okay, so yeah, can we denote area as a number if we state it such as, yeah, but you need to tell me what is A1, right? You probably want to write down A1 equals something, because a lot of time if you give me A1 and you just draw in the picture, but then it's not clear what's A1, right? Because sometimes it's not clear. You need to, you want to, once you write down A1 equals area ABCD at in some place, right, in the corner, then you can move on using A1. Yeah, that's fine. But you need to be clear what A1 stands for. Because if you just put it in the picture, it may not be clear to me, because, I mean, it may be area of something bigger or smaller, depends on the graph. Okay, so I think I'm going to stop here because I realized that my computers keep like freezing and jumping around. So I don't think that it can like handle any more or longer thing. So the last thing I want to say that please read the remaining part of the section 7.5 before Wednesday. This is going to help you. So the second thing I want to talk about is proposition 46, which is a construction proof, construct a square here. And after we do that, that would be the first thing I will do on Wednesday. After we do that, then I'm going to move on to section 7.6, which is essentially the very important Pythagorean identity. Okay, so do me a favor, if you have time, please read in advance, especially the 7.6, especially the Pythagorean theorem. We are going to do 2 kind of proof. The one that in the textbook is more algebra, not more algebra, more geometric, okay? So it can be complicated. So it will be very beneficial if you read the proof for Pythagorean identity in advance, then you will know exactly what's going on here. Okay, so I'm going to stop here. If you have any question, you're free to stay, or otherwise you're free to go. Yeah, sorry about the freezing thing. I don't know what's wrong with my computer today. Thank you.
So can you go up to that proof real fast? What were you trying to prove again? Sorry,
say again?
What were you trying to prove again with all this?
Oh yeah, so I'm saying that the off diagonal. So first you have ABCD, right? The biggest parallelogram, and you draw a diameter AC, and you draw another parallel line EF, and another parallel line here GH. Okay. Then you're going to have some of the area like this, what you saw. So what I want to prove is EKBG, the area of EKBG is the same as area of HKDF. This is exactly this is what I want.
Showing that the complements are.
Yeah, the complements are equal.
Okay.
Yeah.
Okay.
I think, thank you.
Yep.
And how do we know that they're the complements? Are they just the
Oh, this is by essentially by definition. So first you have a parallelogram, right? You draw a diameter, right? So if you draw another parallel lines, right, whatever, that if you have this, right, then this would be the complement. Okay.
Okay, so whatever ones aren't going through.
Yeah, whenever the ones that like off, right? Off, okay. Yeah.
Thank you.
Yep. I need to stop this. It's going to freeze every time. Okay. Any other questions?